Good morning, everyone. We will start with the next topic where we will discuss about the different transforms. So the first one is Fourier series, Fourier transform. Then we have discrete time Fourier series, discrete time Fourier transform, discrete Fourier transform, Laplace transform, and Z transform. So Fourier series, as we all know, uh, what do you mean by Fourier series and why it is important? Fourier series is important because we can analyze any periodic signals. Okay, so we have already discussed that there are two basic periodic signals. The first one is the sinusoidal signal and the second is the complex exponential signals. Okay, now this is the equation for the Fourier series. So if you see, we have xt, which is given by summation of k equals to minus infinity to infinity ak e to the power j k omega naught t. Okay, so here if you see here we have complex exponential signals, which are again periodic signals. So from here, what do we get? We get that any signal, any periodic signal xt can be represented by the summation of various sinusoidal waves or different frequencies whose amplitude can be can also be varied by varying this value ak. Okay, so another form of this Fourier series equation is xt equals to a naught plus summation of k equals to 1 to infinity 2 of b dash k cos of k omega naught t minus c double dash k sin of k omega naught t. Okay, again over here if you see the signal xt, which is periodic in nature, which we consider as a periodic signal, they can be constituted of various sinusoidal waves. Okay. So here one example of square wave has been given. So the first one is the square wave, and then uh, we can see one sinusoidal wave has been added. Then a series of sinusoidal waves have been added, and slowly, when we are increasing the different sinusoidal waves or different frequencies and different amplitudes, and we add those up, the reconstructed signal, it is similar to that of the this pulse wave signal. Okay, however, if you see at the what you call constant amplitudes, whether it is zero amplitude or the high amplitude value of the square wave or the pulsed wave, we are having some corrugations. These corrugations are regarded as ripples. Okay, and then apart from that, at the discontinuities we have some increased amplitude values, and these discontinuities, these are regarded as Gibbs phenomenon. Okay, these discontinuities, they are regarded as Gibbs phenomenon. Now why this is happening? This is happening because the answer lies in the equation itself. If we look over here in the Fourier series equation, what is happening is that we are saying that infinite number of sinusoidal waves, they are being used for the reconstruction of any periodic signal. However, in practicality, use of infinite number of signals is not possible, and due to this reason, what happens is that the reconstructed signals, they are nearly similar to, or you can say not nearly, you can say similar to the pulse wave, but it is not the same. Okay, and this is because the reconstruction of the signal, it is being carried out using finite number of sinusoidal signals. Okay, similarly, if you have a sawtooth wave, again we can generate the sawtooth wave by adding up various uh, by adding up sinusoidal signals of various frequencies and amplitudes. Now coming to the Fourier transform, so all of you know that Fourier transform, it is being derived from the Fourier series itself. However, if you look into the Fourier series, we discussed that the Fourier series is capable of analyzing periodic signal. Okay. On the other hand, Fourier transform, it is used for anyone? It is used for the analysis of what kind of signals? Aperiodic signals. Is it correct? It is correct. Anything else? Anyone? Yeah, it is capable of handling both aperiodic and periodic signals. Why? Can you explain? Why periodic and aperiodic? If we consider the Fourier transform, the first assumption what we get is that a non-periodic signal may be assumed as a limiting case of a periodic signal where the period of the signal approaches infinity. Okay, what is the period? So in our last class, one of the last classes we have discussed that a periodic signal, it is being given by xt equals to x of t plus capital T, where capital T is the time period. Okay, so whether you add or deduct the time period for a periodic signal, the signal would be the same after you add up the t or deduct the t, right? Now here what is called, it is regarded as that any aperiodic signal, they are being regarded as periodic signal. And how they are regarding as the periodic signal, they are saying that the signal is periodic at capital T tending to infinity. Okay, at capital T tending to infinity. When the value of capital T is infinite, then we regard this the even the aperiodic signal as the periodic signal. Okay, so with this assumption we start. Okay, so say for example, if you take a periodic signal, since it is ever continuing, okay, right? So what happens at capital T tending to infinity also, it will be periodic. Okay, I don't know whether you got my point or not. Suppose we have a sinusoidal signal like this. So if you consider this t period, then what happens? It is periodic. If we move this t to the next t, it will be periodic. Now from here to here, if you take, it would be 2t. If you take that period, it will be again shift the signal towards the right or towards the left, it will be periodic. Similarly, if you go for 3t, it would be periodic. Similarly, if you go for t tending to infinity, it will be periodic. So when we talk about periodic signals, so what is happening, even if we consider that capital T is tending to infinite, then also the signal would be periodic. However, in the case of aperiodic signal, what will happen? We are at small time durations, the signal would be non-periodic or aperiodic. However, we are considering that, or we are assuming that capital T is at capital T tending to infinity, the signal becomes periodic in nature. Okay, so with this assumption we start the derivations. I am not going into the derivations, you can look into the derivations later on. So with this assumption, as we start the derivation, we get to the Fourier transform. Okay, and then again for any specific transform, you would have an inverse transform, and in this case it is the inverse Fourier transform. So when we apply the Fourier transform on the signal xt, we get to the frequency domain, and when we apply the inverse Fourier transform on which component we will be applying, we will be applying on the capital X j omega. When we apply the inverse Fourier transform, we get back to the time domain signal. Okay. So this figure, it is self-explanatory. So what happens is that we are having the signal. If we apply the Fourier transform, we get to the frequency domain. क्या हुआ आपको? You want to go? Okay. If you want to go, you may leave if you are not feeling well. And if you want someone to accompany you, you can take someone who will be. Okay. So, yeah, once you go to the frequency domain, then again, if you apply the inverse Fourier transform, you get to the time domain. Now, why this? Why we are interested in first going from time domain to the frequency domain, and then again from frequency domain to time domain? Why this is so? This is because I hope you have started doing this biomedical instrumentation laboratory. You must have seen that when you are taking some signal, what happens? You are getting time versus amplitude plot. But what are the frequency components hidden in this plot? We don't know. So if you apply the Fourier transform, so what we get is that we get a frequency versus amplitude plot, and at whatever frequencies the signal components are there, monotonous frequency components are there, you will be getting some amplitude values over there. Say for example, at 50 hertz, at 100 hertz, I'm just giving you an example, okay? 150, say 200, okay? Now say for example, you got this signal and you can see that you are having a 50 hertz. So you might be having some corrugation over here. So you don't know whether these corrugations, which are basically the noises, uh, it is a 50 hertz noise or not, you don't know. So how do you ascertain that what type of noise is there? Okay. So in that case, when you do the Fourier transform, you will see that apart from the signal components which are present in the signal, you also have a component or an amplitude at 50 hertz. Okay. So from there, you can say confidently that this signal, it is corrupted with 50 hertz power line interference. Okay. Now, once you do that, what happens is that you can apply band pass filters over there. You can design the filters as per your wish, and you can use those filters, and you can eliminate the noises as per your requirement. Okay, you may eliminate the band pass filter. You can use band stop filter. Okay, you can use band reject filter depending upon the frequency components that are present. Okay. Now, what happens? Suppose you have applied the signal component, you have analyzed the signal. Okay. Now you have seen, okay, after band pass filtering, this 50 hertz noise is not there. But in real life, we cannot work on this frequency domain, because in real life, what is our continuous variable? Independent variable. Independent variable is time. So we are habituated to analyze the signal in the time domain. So to look at the image or the signal component which we can perceive and analyze in a better way, we again need to go back to the time domain signal. Okay. So this is the need of Fourier transform, and this Fourier transform, it has been used in most of the scientific fields. You talk about geology, you talk about seismology, you talk about medical imaging, you talk about space industry, wherever you want to discuss, wherever there are any digital processing is happening, you will find that Fourier transform it is helping us in some way or the other. Okay, so it is till date one of the most robust transform, and it has not been replaced with any other transform for analysis. Okay, so you can see it has been there for since ages. So you can understand or appreciate the importance of Fourier transform, okay, in signal processing. Now the thing is that, so these are the periodic and aperiodic signals it has been shown. Yeah. Coming to this system, we have discussed about the LTI systems. When we talk about the LTI systems, if we give an impulse input, if we give an impulse input to the system, we get impulse response of the system. This is impulse input. When we give impulse input, we get impulse response. Impulse input means we have already discussed about delta t. That means at t tending to at t0, we will be getting an impulse. Okay, that's it. So when you do that, at 0 instance you get the input and you get the output. So this output, it is called impulse response, and any system, whether continuous time system or discrete time systems, they are regarded as its characteristics are being described by this impulse response. It is specific for a given system. Okay, now when we have an input xt, if we give the input xt to an LTI system having an impulse response of h of t, then we get or we can predict the output yt, which is given by xt convolution of ht, xt convolution of ht. Okay, now convolution, it is slightly mathematically tedious form. So what it is being done is that if we take the xt input and if we perform Fourier transform, we get to x of omega. Similarly, if we have ht, if we perform Fourier transform, we get h of omega. Okay, we get the input, and herein we get the output y of omega. It is equal to x of omega multiplied by h of omega. Okay, so we have got the output in the frequency domain, and then when we apply inverse Fourier transform, we get the yt over here. Now performing multiplication is much easier as compared to the compared to performing the convolution. Okay, so many a times you will find that this approach is being followed. I mean to say that the output is being computed in the frequency domain, and then through inverse Fourier transform we get to the time domain signal. Now coming to the Fourier analysis of the discrete time signals. So just like the continuous time signals, for the discrete time signals we have discrete time Fourier series. So the first one is the synthesis equation and the second one is the analysis equation. Again over here if you see the similar equation you will be having, see these complex exponentials are there, which are periodic signals. So any given signal, they are basically computed of a series of sinusoidal signals of different frequencies. Okay, because if you see k omega naught, it is varying. K omega naught, it is varying. Now, coming to the discrete time Fourier transform. So, similar to the discrete time Fourier series, normal yeah, Fourier series to Fourier transform, we had some transition. Similarly, in the discrete time Fourier series to discrete time Fourier transform, also the same hypothesis is being applied, that discrete time aperiodic signals, they have an what you call time period which is tending to infinity. Okay, over here also, if you see, we have discrete time Fourier transform and inverse discrete time Fourier transform equation. Now, in the discrete time Fourier transform equation, what you are having, again, see, addition of some complex exponentials of different frequencies, right? Now, if you look into the IDTFT, what is happening? We are having an integration. Okay, we are having an integration. So integration, it is a continuous process, it is applicable for the continuous process. So even though we are, for the forward transform, we are using the discrete equation, but in the inverse transform we have to use a continuous function. We have to use a continuous function, right? Now, the digital systems, they are not able to handle the continuous functions. They can only handle finite systems. Okay. Due to this reason, there was a need for another transform, which we call as discrete Fourier transform. Okay. We will come to that. Just before that, the same analogy what I discussed about you some time ago, that if you are having an LTI system, then its input output relationships, how we can do it in the discrete time domain using the same analogy. This you will be able to appreciate the input output relationship of the LTI discrete time system. Okay, the same analogy, it happens over here. So we have the xn, we have hn, then we are having output as yn equals to xn convolution of hn. Okay, then similarly we can convert it into the frequency domain, and then we can get the output y of omega, and then we can perform inverse Fourier transform in order to get to the time domain signal. Now the problem, I have already told you that in discrete time Fourier transform, what we are having? We were having that the inverse discrete time Fourier transform, it was implementing integration, which is a continuous function. Now, due to this reason, the transform could not be implemented in the digital systems. Now, due to that reason, this discrete Fourier transform, it was then developed. Okay. So, what does that mean? What does that mean? So, if we go back to the previous equation, x of omega, it would be discrete in nature, but x of n, it would be a continuous time signal. Okay, but the problem is that we are not able to implement these transforms in the digital systems. So we need a transform where, or the values where which would be discrete, and those discrete values would be handled by the digital systems. Okay, so that means we have to convert this continuous time domain into the discrete time domain, and this is what this discrete Fourier transform is. This is a very good chart. Okay, this is a very good chart Hence, what is happening in discrete Fourier transform? So, we have a signal in the time domain. Okay, we have this signal. So, it's corresponding. If you perform the Fourier transform, its corresponding frequency domain component, it is given over here. Okay. So, what we are doing? Discrete time Fourier transform. Initially, we are having discrete time signal. So this continuous time signal has to be converted into a discrete time signal by the process of sampling. So this is the impulse train. Okay, so this is the impulse train. So when you multiply these two, we convert this continuous time signal to a discrete time signal. And if you look into the frequency domain, we have the frequency component of the signal. The Fourier transform of an impulse train is also an impulse train. It would be something like this. Okay. So if you see, we are giving multiplication over here. So if you see, now as soon as we get this discrete time transform, and if we perform the Fourier transform over here, what we get? We are getting frequency components which is repeating itself. The original frequency component, it is repeating itself. Why? Because in the time domain we have multiplied, however in the frequency domain it gets convoluted. Okay. For calculating the output of the LTI system, we saw what we saw. Convolution was in the time domain and multiplication was in the frequency domain. So the vice versa also happens. If we perform convolution in the frequency domain, you get multiplication in the time domain. So here in the time domain we have done the multiplication, and due to the convolution factor, what is happening, this frequency component, it is repeating itself after every 2 pi. Okay. Now since it is repeating itself, what we have to do, we have to take the continuous time signal which is band limited. Okay, which is band limited. Why? Because if you do not limit the band frequency component, say for example, say 0 hertz to say 100 hertz, if you do not do it, then what will happen? When it is repeating itself, then there would be overlapping. So say 0 to 100 would be there, and again some components which are repeating itself, they would overlap with the system. Okay, so when we are doing the sampling, we have to band limit the signal before going for the this uh, before going for the sampling. Okay, now why it is done? This is because of a criteria which is regarded as Nyquist criteria, which says that the sampling frequency should be greater than equal to 2 of maximum frequency. And as I told you, any continuous time signal, it is having infinite number of sinusoidal signals. So frequency components above this FM would also be present. So to make our system capable of handling whatever the signal component you are trying to analyze, we have to band limit the signal such that this Nyquist criteria, it is being followed. Okay, the Nyquist criteria, it is being followed. Okay, so you have to choose the characteristics of the impulse train which is related to the Fs, because that this impulse strain, how much will be this delta t, it would govern what is your sampling frequency. 1 by delta t, small 1 by delta t, it is your sampling frequency basically, right? So to get this sampling frequency, at what sampling frequency you will be sampling the signal, you need to know the fm. But for a continuous time signal, we have the fm equals to infinity, which we cannot handle with our digital systems. So because of this reason, we have to band limit the signal, so that in the frequency domain, when the frequencies are repeating itself, they do not get overlapped. They do not get overlapped. Okay. Okay, this is done. Now what? Now we know that the signal what we have got is this one. Now herein, if you see the frequency component, it is continuous in time. Okay, so it has to be sampled. Okay, it has to be sampled. Now since it has to be sampled, so in the previous case, if you see, when we are sampling in the time domain, we went for the band limiting. Similarly, when we would be sampling in the frequency domain, we have to time limit the signal. Okay, we have to time limit the signal, so we will be using a filter window, which is basically a window, to get a section of the signal, and once we get that, we got this time limited signal. Its Fourier transform is like this itself. See, it was quite smooth over here. After time limiting, it has got somewhat wonky. Okay. Now, once we have time limited, we can go for the sampling in the frequency domain. Now, once we have sampled in the frequency domain, see the time signal, it is repeating itself. Okay. So, band limiting and time limiting are of utmost importance when we discuss about this discrete Fourier transform. Okay. Now, in this case, if you see, both the time domain signal and the frequency domain signal, they are they have been discretized, and since they have been discretized, we can uh, go for the this we can use both the signals in the digital system, both the forward transform and the inverse transform, and we can implement that in any of the digital systems. Okay. So this is the uh, so if you look into this these equations, DFT and IDFT, so if you see both of them, they are now discretized. Okay. So herein, if you see, there is one equation, one component W K N N, and it is regarded as Twiddle factor. And this Twiddle factor, it is given by this Wn equals to e to the power minus j 2 pi divided by n. And if you talk about the Kn, so it becomes this one multiplied by k. Okay, it goes in the numerator. Okay, so using this factor, we can go for the calculation of the DFT and IDFT. Now, if you see these two factors, in DFT it is normal twiddle factor, in IDFT it is the conjugate of the twiddle factor because of this minus sign. Okay. And if you see, there is another minus sign over here. Now, how to calculate the twiddle factor for any given twiddle factor? So what you have n k. So you have 0, 1, 2, 3, so on. Then you have 0, 1, 2, 3, and so on. Say n. Say here also you have n. Okay. So Wn, what would be nk? 0, 0. Similarly, here 0, 0. At this location 1. At this location 1 multiplied by 2. At this location, see, 2 multiplied by 1, 2. At this location 2 multiplied by 2, 4. Okay. So this would be your, in the matrix form, this would be your calculation for the DFT, and this would be for your IDFT. Now herein in the IDFT, if you see, 1 by capital N component is there. So capital N is the signal length. Okay. So total factor matrix, if you try to find out the modulus of this one, e to the power minus j theta, what it is? It is basically a cos theta minus j sin theta. If you find out the modulus, it is your um, uh, modulus of a circle. Okay. So from there, how can we get the information? What should be the total factor matrix? Okay. So for W2, capital N equals to 2, let's find out the total factor matrix. So 0, 1, 0, 1. So over here it would be 0, 0. Over here it would be 0, 0. Okay. So what happens is that in the previous case we have seen that we are having an amplitude of or a no, we are having an equation of a circle. So let's go into the complex plane where we have x-axis as the real and y-axis as the imaginary axis. So in that axis we are having a circle. Okay. So in over here what we are having basically, we need to have 0 this thing. So 0 component by default it is the 1. So y1, if you again go back over here, if you put nk as 0, this whole component would be 0. e to the power 0 is again 1. Okay. So anything to the power 0, it is 1. So blindly we will put 1, 1, and here also 1. Now second one, what we have to do, we have to, it is a 2-point DFT, and this circle it is having 360 degree. So 360 by 2 is 180 degree. So 180 कहाँ पे है? इधर है. So the values would be -1 at this point because we are on the real axis. Okay. But the question is, should we go in the anti-clockwise or should we go in the clockwise direction? Okay. Why? What would give us the information? This minus sign would give us the information that if it would have been positive, we would have gone in the anti-clockwise manner. However, since we are having a negative at this point, we will be going in the anti-clockwise direction to reach to the point 1. Now coming to the WNK4, again 0, 1, 2, 3, 0, 1, 2, 3. Similarly, we will be dividing it into 4 points. So 0, then we will go to the, क्या होगा, 360 by 4, 90 डिग्री यहाँ पे आया, then 90 इधर, then इधर, then इधर. So if you plot this thing, if you see 1, 2, 3, 4, 6, 9, we are having total factor values up to 9. So कहाँ से शुरू होगा? 0, 1, 2, 3, again 4 will be equals to 0, and it will be repeating like that. So in this way, when we get these values, we just have to put the value over here to get the total factor matrix. Okay. Similarly, we can calculate the total factor matrix for 6-point DFT. Okay. Now, another important thing which I forgot to tell you is that if you see over here, the values, they remain the same, and you only have the conjugate, only the sign changes. If you go over here, here also if you see, the sign is only changing. Okay. Now coming to the 2-point, 4-point, 6-point and 8-point DFT. Suppose we are having a signal of x of n 2 0. So what we have the total factor matrix. Then we have 2 0. Solve it. We get the frequency component as x of k 2 2. Again, if you want to go back to the original signal x of n 1 by 2 multiplied by conjugate of total factor. यहाँ पे कोई complex number है नहीं. We do not have any complex number, so there will be no change in the total factor matrix. Then we are having this signal component which has been put over here. You solve this, you get back to 2 0, which is your original signal. Now, if you see, I am telling that DFT is performed for 2-point, 4-point, 6-point, 8-point, all the even digit numbers. Since basically xn, what I have given, xn I have given as 2, right? So to make it even, we have to pad the signal with 0 to make it a 2-point compatible signal for 2-point DFT. Similarly, if I ask you to perform 4-point DFT, then you will be adding 2 more zeros to make it compatible for 4-point DFT. Again, total factor matrix we have calculated. You just put the values, you get the thing. Again, you can perform the inverse Fourier transform and you can go back to the original signal. Now, what is happening over here? 2-point, 4-point. Here also you have got some DFT values. Here also you have got some DFT value. Say for example, you are having a window, and on the other side of the window you are standing, and within this window we have made it black. So what I am doing at the first instance, I have given you just two slits through which you can watch, and you are having the scene over here, right? Now through this scene you are only able to see these two portions. Okay. Now when I go for the 4-point DFT, what I am doing, I am giving you 2 more slits. So correspondingly you are able to see more information. Okay. So as you go on increasing the number of points, capital N signal length, if you increase, you will be getting better resolution of the frequency axis. Okay. Your original signal, it will not change. It is xn equals to 2 and xn equals to 2 comma 0 and xn equals to 2 comma 0 0 0. All are same. The signal remains the same, but the information about the frequency axis what you get, it is far better. Okay. Now another important thing, if you see 2-point DFT for xn equals to 2 2, we have x2 equals to 4 0. Okay. In this thing, if you see in 4-point, these values they have added up. Herein 2 more components have been added. Okay. When we go for the 6-point DFT, these are there, but these 2 points are not there because we have changed the window positions. That's why these 2 positions are not there. However, as we go towards the 8-point DFT, if you see these 2 points, they have also appeared. Total factor matrix जैसे हमने ये किया है, you have to calculate for the 6-point DFT. I have already told you, shown you how to calculate. Similarly, you can also calculate for the 8-point DFT. You have to calculate the total factor matrix and then you can go. And then herein there are some examples, but you can take a note of this and you can do it on your own, try it on your own. Okay. So this two. So in the next class, I will start with fast Fourier transform, which is not a transform in itself, but it is an algorithm to implement DFT in a faster way. Okay. Do you have any questions? No. Okay.